So architecture and hyperparameters as well. By now you should be a bit familiar with terminology, number of layers, number of neurons, all that, learning rate, etc. But of course we have to make choices as to what this would look like. And one of the choices that you have to decide upon is the depth of the network. So as I already mentioned, especially the earlier networks were shallow, one layer, two layers. Implementation of the backpropagation algorithm by hand made things tedious if you wanted to go further than that, but also some of the other things that we encountered before, like the vanishing gradient problem, especially when people were still trying to do everything with sigmoid functions inspired by nature, where you have this threshold in the neuron response. Um, you will have this vanishing gradient problem very easily, especially if the size of the network builds up and all of these things start to get multiplied. These gradients start to get multiplied with each other in the chain rule as well. You very quickly get that anything goes to zero. So luckily the emergence of ReLU as the typical activation function changed that a little bit. But it's still a choice, of course, that you have to make. Do I have to be shallow or should I be deep in the choice of my network? Um, Also, the width of the network is an important aspect. How many neurons do you actually put in each layer? When it becomes the number of layers in the network becomes more than two, we would typically be referring to deep learning. Briefly touched upon before as well is the complexity of the network. So do you have a dense network in which all of the neurons of one layer are connected to all of the neurons in the next one, or will you have fewer connections because well, you know that your applications are facilitated by that, and then of course you also have fewer weights to train. Or do you actually have connections between non-directly connected layers as well, going around some of them? Um, so when it comes to generalization, one of the things that has been empirically observed by now is that deep networks can typically generalize better. Because the idea behind a deep network is that when you want to, your output basically describes certain features of your input. When you only have a single layer, there's only so much that you can do. So it can only basically work on the on the characteristics of the data that are already in your input. In the early days of neural networks for classification, it was a major limitation. And what you started seeing is that people would do feature engineering. So they would have an image that they would analyze, but because they only had one or two layers to work with, they already had to manually extract certain features of the image to provide to the network for the network to be able to classify them, because they didn't have the appropriate architecture to really be able to extract the features from the image itself. And as we will see in the computer vision lecture, by building a lot of sequential layers that all basically reduce the dimensionality of the image, but look at the emergence of things like edges in the data and how these edges are interrelated to each other, you can automatically extract these features from images. So you don't need to manually do that. But you need to have a certain depth for the network to be able to recognize these features and in order to associate them accordingly to really be able to classify something. So these are these intermediate features that I refer to here. And these require a certain depth to be able to recognize. And basically the depth and the width of the network are hyperparameters in themselves. So for certain chemical engineering applications, a few of them which we see later, you might not need that depth in order to have a properly functional network. And then of course a shallow one is easier to train, it's faster to train. It requires less data probably to train, but it might not generalize very well to other applications. So that's also an aspect for you as a user. Do you want something that works well for a particular application? You might get away with a shallow one. Do you want one that's very general? You probably need to have quite a deep network. Of course, it also relates to, once again, underfitting and overfitting. You know this from the previous lecture, right? So I won't really spend too much time on it. But yeah, basically you want to be somewhere in between, right? Generalization means that you capture the data properly, but also you don't mesh data exactly because then it doesn't properly translate to other applications. And we once again get into the validation of your network as well. So you set up your method such that your loss function will decrease with over the epochs as a function of your training data. Ideally, you would have a very low loss function upon your training. As your model complexity increases, you will probably achieve that because your model is better able to fit to the particular characteristics of your data. But you can run into a problem that if your network becomes too large, there's so much freedom that it starts being specifically tuned towards the data that you put in the training, but it doesn't generalize very well anymore. So your validation data set, you might see the loss function go up. And then, of course, you want to tune the parameters in your network accordingly to also make sure that you get a good match in your validation data. That's the purpose of the validation step, to tune the hyperparameters of your network in order to get a good balance between complexity and proper reduction of the loss function on the validation data as well. This we also saw the last time. You typically, if you have a data set, you want to divide it in 3 epochs, so the training data to actually calibrate the weights of your network, the validation data to calibrate the hyperparameters of your network, so to check if the network architecture is actually correct. And then the test data, finally, that if you have your network and the architecture completely set, you want to show that it works for another independent set of data once again. Of course, all of this is requiring quite a bit of data in order to conduct. And you might, especially in chemical and biochemical engineering applications, data is expensive. It's not as all the things that are going around the internet where you just scrape the entire internet for your data. There's typically rather limited amount of sensors in the plant, which might be giving you a very local perspective of your data. Lab experiments are expensive. If you work with cells, you might have 10, 20 fermentations going on in the different conditions, but probably not much more than that. So if you want to know how your cell responds to different conditions, you have a very limited data set. Yet we want to apply these kind of methods which are very data hungry. So can we be efficient in the usage of our data? Well, there actually are methods to get around this a little bit where you have to work with limited data sets. And one of them is this cross-validation technique, where within a limited data set, of course, you need to pick a certain amount of data for your testing application. But instead of just dividing your whole data set in a training and testing data set, you go through your data multiple times, and every time you assign a few different cases as being your test data and use the rest for training. And in that way, you do have slightly different tests every time, so you avoid the generalization aspect, but you can get away with a somewhat smaller amount of data in total. So this is one technique where you can where you can deal with relatively small amounts of data. Still, typically, you will need to have an appropriate data set in order to train a network in the first place. So don't expect some magic from doing this type of method. All right. Of course, you can play around with this a little bit as well if you so desire.